Okay, let's get started. Good morning, everyone. So, okay, so still I can find many empty seats here. Okay, so we make puppies the next class. So puppies is a kind. It's called in Korean. So it can be called 족지시마. That is just a very simple. So I will just show the very simple questions, like maybe 3 or 4 questions, and then so actually the answer you can answer with a very simple the word or some very simple, maybe it's the circuit. So I don't know, but anyway, actually, so in this course, I plan to take 3 or 4 pop quizzes. So just quiz, not it's not serious. Okay, it's not serious exam. Okay, so it's just a quiz, but actually, so I believe you need to study for this course during the semester, and then also you need to actually actively participate in the class. Okay, so that's why sometimes I take the pop quiz. So I prepare the pop quiz in the class, but I made it. Okay. So what did we learn in the previous class? Okay. So we learned about the axioms and then some theorems of the Boolean equations. And then, so that's my expectation, but I believe so you can easily understand the axioms, because so axioms are very simple, and then we simply think that axioms are just true, right? So it's just true. So we don't need to prove the axioms, and then we can also learn about the several theorems of the Boolean equations, like the identity, as you can see, so like T1 to T5. So actually, from T1 to T5, so these theorems are also very simple, right? And then it's obvious. Okay? And then, so for the T6 to T11, so those theorems are a little bit maybe it's a little bit complex. Okay, complex. So it's a little bit tricky, but I think so. Actually, the property and the theorems of the Boolean equations are similar to the theorems of our normal equations, right? Like the commutativity, associativity, and then distributivity. So actually, we already know about. So I believe you already know about these properties of the normal equations, right? Like so a plus b is b plus a. The a multiplied by b is the b multiplied by a, and then it's obvious, right? And then if we just think about the circuit or basic logic gate, so actually, so think about the AND gate like this. A, B. Actually, this is equivalent to the B and A, right? Because we actually there are no priorities, or there are no orders between the two inputs of the basic logic gate, and or then door, and then some other logic gates. So we actually we do not have any orders or priorities for these basic logic gate. So commutativity is obvious, and then associativity is also so obvious actually. So actually we can easily understand some associativity problem. So as I mentioned, So I mentioned that the inputs for the basic logic gate do not have any orders or priorities. So it means that the associativity is also obviously true. Okay, and then we can also apply the distributivity, and then so it's very it's obvious in the normal equations. And then actually this is different because as I mentioned, AND gate and OR gate is just a gate. It's not it's not multiplier. Okay. So actually in a normal algebra, the adder and multiplication, addition and multiplication is different, right? But actually, and also we can observe some priorities, right? Like the priority of multiplication is higher than the priority of addition, right? But actually, between the AND gate and OR gate, so actually these are hardware gate and then hardware logic. So which means that actually this equation like P plus and then C multiplied by P. So actually this is the P or and then C and D. So actually it's just a gate. And then we can apply some distributivity theorem for this and or gate. Okay. And then covering and combining and consensus. So using some basic theorem and then basic axioms, then we can prove covering and then combining and consensus. Okay. And then so I mentioned that this Tomorrowland theorem. So Tomorrowland theorem is the unique theorem of the Boolean equation, right? So and then actually so it means that this is critical. This theorem, the Tomorrowland theorem, is important. Okay, so so this is the Tomorrowland theorem, and then so actually you need to memorize this. Okay, but so it's just simple, right? So like this. So in the Tomorrowland theorem, the bar, which means that this is the equivalent symbol, right? So this is the and then you can find the bar of A and B. So this is the NAND gate, right? Actually NAND gate, right? So bubble is here, but for this circuit, we can push bubble to the input of the gate, and then we can change the AND gate to the OR gate. Okay, so this is the Morgan's theorem. Okay, so like this. So and the bar of the AND gate can be replaced with the bar of two inputs and OR gate. Okay, the OR of the inversion of two inputs. Okay, this is the De Morgan theorem. And then I also mentioned that actually we use De Morgan theorem frequently because we can optimize the CMOS circuits using De Morgan theorem. Okay, so I just come so in the previous class, so I just compare the number of transistors required for implementing the logic gate, right? So for the NAND gate, so this is the NAND gate, so we require 4 transistors, right? And then for this inversion of input and OR gate, actually we require 10 transistors. Okay, so this is better because we can use less number of transistors, right? So we can invest a smaller number of transistors for implementing a certain Boolean equation, like actually, and so basic gate. Okay. So actually, So we can easily understand the behavior of AND gate and OR gate, right? Because this is the kind of true logic gate. So which means that actually the output of this AND gate and then the output of OR gate is not inverted. So we can intuitively uh, calculate the output of this AND gate and OR gate easily. But then, and then NOR gate, so as you can see, this is the, these gates includes bubble, so inversion of the output. So sometimes, so it can be more tricky to understand some behavior of this NAND gate and NOR gate, right? So, but actually, if we use NAND gate and NOR gate, so we can reduce the number of transistors for for implementing the digital circuits, right? So I explained the reason, right? So because we cannot implement the AND gate directly. So actually, we need to implement the NAND gate and inverter. Okay, so and then so AND gate requires the 6 transistors because of this issue. So with the De Morgan theorem, then we can just switch. We can just replace the AND gate or OR gate with the NAND gate and or NOR gate, right? So that's why we use the Morgan theorem for optimizing that is the circuit, but CMOS circuit. Okay, so that's why the Morgan theorem is the important theorem in the Boolean equation. Also, this De Morgan theorem is the unique theorem of the Boolean equation. Okay, so I quickly explained about this. So actually, so we can change this circuit to this right-hand circuit using the Morgan theorem, right? But actually, this is the optimized circuit. So as you can see, this left-handed circuit includes the NAND gate here. So NAND gate, that's a NAND gate. So how many transistors are required? Four. So thoroughly, for implementing this circuit, we require 12 transistors, right? Because for the NAND gate, we require 4 transistors. But we can apply the Morgan theorem, and we can change the basic logic gate. Okay, so firstly, we can focus on this logic gate. This is the NAND gate. So then, as you can see, the bubble is here. The bubble is here. Bubble is at the output port of the NAND gate. Okay, because this is the NAND gate. So if we just apply the Morgan theorem, firstly we push this bubble to the inputs of this AND gate, right? So it's here. The bubble is pushed to the input port, right? And then AND gate is changed to the OR gate, right? So this is the De Morgan theorem. Okay. Then we can observe the bubble is here and bubble is here and bubble is here and bubble is here. And then in this circuit, this is the node. Okay, this is the node. And then in this node, you can find two bubbles, so it looks like the not bar of bar A, right? So actually this is A, right? Because so double inversion, so this is equivalent to the original signal. So actually we can delete this these bubbles. So if we see that this change this circuit, then we can find that this is the simple AND gate and then simple OR gate. Okay, because the two bubbles in the same node can be removed. Okay, so it's a bar of a bar. So inversion of inversion is same to the original value. Okay, and then we can easily understand the actually this circuit because so we use the AND gate and OR gate. Okay, this is the very basic form of the SOP form, right? Sum of product form. The firstly AND gate and then the output of AND gates are ORed. Okay, so this is the SOP form, right? So we can easily understand the SOP form, right? But actually, if we just consider the number of transistors, so how many transistors are required? Is 6, 6, and 6. So totally 18 transistors are required for this circuit, right? So actually, we can apply the Morgan theorem. So actually, firstly, we can build very basic SOP form of the Fourier equation. And then, also I explained that so using SOP form, we can build all Boolean equations. So which means that all Boolean equations can be represented as the SOP form. And we can easily understand some behavior of this Boolean equation represented by as SOP form, right? But actually this logic is not optimized. This circuit is not optimized. So we can apply De Morgan theorem to this direction. Okay. So we can change the uh, this AND gate to the NAND gate and then OR gate to the also NAND gate. Okay. By applying De Morgan theorem, then we can reduce the number of transistors. So we can reduce the cost. Okay. Okay. So optimization is required. So firstly, we can build a very simple SOP form or POS form of the Boolean equations. And then, if possible, then we need to optimize. So we need to simplify these Boolean equations using axioms or theorems. So why? Because if we just use a simpler Boolean equations or simpler Boolean equation, then we can use less number of basic logic gates. So which means that we can require the less number of transistors. Then if a certain circuit includes the less number of transistors, then we can reduce the cost, so manufacturing cost. Okay, so by applying some theorems or some optimization technique of for the Boolean equation, then we can optimize. We can simplify our the system, what is the logic. Okay, so as you can see, simplifying could also mean fewest number of gates. So we need to reduce the the number of gates or lowest cost and then lowest power. Okay, it is directly related to the cost, like the manufacturing cost, right? Because if we use the smaller number of transistors, then we can reduce the manufacturing cost. Also, basic logic gate. So logic gates also consume electric power, right? And then, so which means that if we reduce the number of transistors, then we can also reduce the power consumption. So actually, this is critical. Okay, this is the power consumption issue, and then the manufacturing cost issue, and then power consumption is issue are very critical for our the modern digital systems or modern computer systems. Okay. So this is the example. So and then so you can find several examples in this slide. Okay. So this is very simple, right? So actually this is the combining theorem, like P10. And then so actually this is the y equal b. But even though we do not memorize the this combining theorem, then we can easily simplify this Boolean equation to this equation. Right. So firstly, we can apply distributivity theorem at T8. Then you know A plus A bar. So this is the A or A bar. So this is actually 1, right? So A equal 1, right? How about the A and the A bar? What is the reason? This is 0, right? Because if the A is 1, and then A bar is 0, and then 0, and then A bar is 1. So actually 1 and 0 is 0, right? But for the OR gate, A or A bar is 1. Because one of these terms, one of these terms is always 1, right? So that's why this is 1, so this is B and 1. B and 1 is the B, right? So we can, even though we do not memorize this combining theorem, then we can just simply we can optimize this Boolean equation. Okay, and then this is a little bit tricky. So actually, there are three terms here, three terms here, right? So, but we can simplify this Boolean equation like this. This is the final answer, right? So firstly, we can apply the idempotence theorem here, and then so we can also apply the associativity theorem, right? So this is the, and then by applying combining theorem, then we can simplify the this Boolean equation. Okay, so actually combining theorem. So combining theorem is actually, so it's important. Okay, so which means that we use this combining theorem for optimizing Boolean equation frequently. So actually, maybe the next class we will learn about Kanomet. Okay, so we can use the Kanomet for optimizing Boolean equation also, and Kanomet actually use the combining theorem to reduce a certain term. So if we just apply combining theorem, as you can see, like here and here, so other terms are same, but for the B, so we use the B bar and B here. So in this case, we can make the B bar and or B and AC, and then this term will be removed. Okay, so if we can remove a certain term, then we can simplify. We can optimize the equation, right? So combining theorem. So we can frequently use a combining theorem to remove a certain term. Okay, this is the same. So as you can see, BC is here. This is the common part, and then we can find A and A bar, and then A plus A bar equal 1. So A can be removed. Okay, using combining theorem. Okay. Okay, so actually you can just apply so you can just follow the this simplification process right here. Okay, fine. So so you can find that the associative here and then combining it also applied here. Okay, so we can easily if we just apply, if we just use the axioms or theorems, then we can simplify Boolean equations. Okay, and then how about the De Morgan theorem? So this is the example, right? And then if we just see the this Boolean equation, this equation looks complex, right? So we can find the many bars, the many inversions here, right? But we can start from the outermost the bar to the inner bar of this Boolean equation. So firstly we can apply the Morgan theorem for the outermost bar. So outermost bar is the this bar, okay, this inversion, right? We can apply the Morgan theorem from the outermost bar, and then we can apply the Morgan theorem for the inner bars. Okay, the bar means the inversion, right? So how can you apply? So if we just focus on this bar, then what is the term? What is the input literals for this bar? So actually, if we just focus on this bar, then we can find the AND gate here, right? So and then for this AND gate receive this input and this input, right? Can you follow me? So this is the AND gate, and then bar is the outermost bar is the inversion of this AND gate, right? So how can you apply the Morgan theorem? So firstly, the input, the bar is moved to the input of this AND gate, right? So this is the A plus B D, and then AND gate is replaced with the OR gate. Okay, so this is the Morgan theorem. So this becomes the plus, right? It's the OR gate, and then so this is the another input of the AND gate. So this becomes the C, right? And then this is the actually C, right? So this is the A plus B plus C. Okay. Then we can find another bar here. Okay. And then we can also apply the Morgan theorem, because if we just see this term, then we can find that this is the OR gate, right? And then the bar inversion is applied to the output of this OR gate. Then we can apply the Morgan theorem. So for the C, we cannot find any bar, so we can actually it's just the C, so we cannot apply the Morgan theorem. But for this term, then we can apply the Morgan theorem. Then how? Oh, this bar is moved to the inner bar, the term of the OR gate. A plus B, D, and then the OR gate is replaced with the AND gate. Okay, so what can be put? It will be like this. Okay, and then this is the double inversion. So this is the A, B, D plus C. Okay, so actually this start is the A, B, D plus C. Okay, so when we apply the Morgan theorem, then we can apply the Morgan theorem from the outermost bar of the equation. Okay, right? So here, so fortunately it's true. It's correct. Okay, and then also you can apply the same, so the Morgan theorem for the different equation. So for this equation, you can also apply the Morgan theorem for the outermost bar here. Okay, here. Okay, here, so we can apply the Morgan theorem. Okay, so you can apply the Morgan theorem by yourself. Okay, so actually this is the answer. The answer. Okay, so actually for this slide, this slide covers the chapters 2.1, 2.2, and 2.3 of the textbook. And then please read the textbook. Okay. Okay, so let's move to the different topic of this class. So this is the combinational logic design. So what is the combinational logic? What is the definition of a combinational logic? Output is defined by only input. So output is the function of current input signal. So this is the definition of combinational logic. Also, I explained that combinational logic is memoryless, right? So it is because the output is just determined by the current input. So there is no memory components in the combinational logic. Okay. So first, in this class, we will learn how to design, how to implement combinational logic. Okay. So from logic to gate. Okay. So question. So build the following equation. So this equation is the Boolean equation, right? So build the following equation using logic gate. And how? So if we see that this Boolean equation, you can find y is the output, right? And then actually this is the multiplication, and then multiplication is the AND gate, right? So AND gate, and then also you can find the C bar multiplied by D and then multiplied by E. So these are multiplications, but actually these are AND gate, right? Okay, so these are, and then in the Boolean equation, so multiplication has the higher priority than addition, right? So if we see this Boolean equation, you can find that the output of this term. Okay, so output of this AND gate and output of this AND gate are ORed, right? So we can build the we can build the logic gate like this. So this is the AND gate. Okay. And then this is the another AND gate. Then A, B, but this is the bubble, right? Because you can find the bar here, the inversion. And then C, oh, this is also bubble because you can find the bar here, bar over the C. Then B, E, right? So, and then output of this AND gate is OR. Okay. So this is the equivalent logic gate for this Boolean equation. So we can, so if we just know the definition of Boolean equation, like the multiplication is the AND gate, or an addition is the OR gate, and then bar is the inversion, then we can easily build the this build the logic gate from the Boolean equation. Okay, like this. Okay, so I just use the bubble here, but bubble means the inverter. Okay, so if we just use the inverter, then it's actually same to the bubble. Okay, then so actually this figure is called the schematic. Schematic. Okay, so which means that we can just draw a diagram of a Boolean equation using basic logic gate. Okay, so the basic logic gate has the input and output port, right? And then also we can just connect the input and output ports of multiple basic logic gate. Then we can build the digital circuit. Okay, and then this diagram and this figure is called a circuit schematic. The schematic. Okay, and then these are common rules for drawing circuit schematics. So input on the left, so it starts from the left side, the input starts from the left side of the diagram, and then output on the bottom. So input can be start from the top of the diagram, and then the output can be located on the bottom of the diagram. And then it flow from left to right or up to bottom. Okay, because so sometimes the input can be here. Okay, you can draw a gate like this. Okay, the straight wires are best, but sometimes you can just you draw like the wire like this. Okay, so just to remember that when we draw a circuit schematic using a basic logic gate, the input starts from the left and the output is on the right, and then input start from the top, and then the output can be located on the bottom of the diagram. And then also the wires. The signals, a signal can be transferred via wires, right? So this is the input signal, and then so if we just see this wire, the input signal value, and then actually it's a voltage, but so so we can say that this is value. The input signal value can be transferred to the input port of this AND gate via wire. Okay, so wire is a path that can transfer or that can deliver a certain signals, right? And this is the wire rules. Okay, So you can find the T junction here. So which means that so in this figure, so you can find there are two wires, and then these wires meet at this point, right? And then this is T junction, right? So in this case, we assume that this wire is connected to this wire. So it's wire B and wire B, wire A and wire B. Then at this T junction, the wire A and then wire B are connected. So what does that mean? If this is the input, so if this is the input signal, then this signal can be delivered to this direction and this direction, right? Because at the T junction, two wires are connected. And then if two wires are crossed like this, and then if we just add dot on this cross junction, cross point, then it means that these two wires are connected. Okay, so, but for this one, for this figure, two wires are close to each other, but we cannot find any dot here. So which means that these wires are not connected. So just remember that at the T junction. So at a T junction, then even if we do not add dots at a dot at the T junction, then but these two wires are connected. Okay, at the T junction. Okay, but if the two wires are cross each other, and then if two wires are connected, then we need to add dot at the cross point. But if we do not add dot at the cross point, then two wires are not connected. But this is not recommended. It is because even though this is the rule, sometimes so it can be confused. Okay, so if two wires are cross each other, then but sometimes so we need to first check the dot because we need to check the connection between the two wires. But sometimes we may think that two wires are connected like this, even though this is not true. So sometimes we can be confused. So drawing like this is not recommended. Okay, but just to remember the rule of the wire. Okay, then let's learn about how to build the combinational logic. So we frequently use the two-level logic. Why? So it is because in the previous class we learned about the SOP form, right? So what is the SOP form? SOP form is the sum of product, right? So what does that mean? Firstly, we can make products using min terms, right? And then by ORing, we can apply OR gate for the min terms. Okay, this is the SOP form. So if we just build the logic gate for the SOP form, then we can build the two-level logic because firstly we apply AND gate and then we apply OR gate. So this is the two-level logic. So this is the very common logic design for the combinational logic. So because all Boolean equations can be represented as SOP form, then basically SOP form is the two-level logic. So firstly, we use minterm, and then minterms are OR. So these are two-level logic. Okay, so this is the example. Then how can build the logic gate? How can build this circuit using basic logic gate. It's simple, right? So these are AND gate. These are, for this term is the AND gate. AND gate. So we can first draw AND gate, and then A, B, C. So bubble, A, B, C, bubble, A, B, C, bubble here, and then the output are word. So this is the logic gate for these Boolean equations, but it's not beautiful, right? So we can build like this, okay? So actually it's the same, the equivalent circuit, but it's more beautiful, right? It's more beautiful than this drawing. So we can make literals, right? So literals are A and original value, original input, and then the inversion of the input, right? So A is here, and then by using inverters, we can make the A bar, B bar, and C bar. Okay, and then so input start from the top. Okay, so top to bottom. So which means that if we just see the wires here, then we can find that this wire is the A, and this wire is the A bar. This wire is B. This wire is B bar, C, and C bar. Okay, we can make if we just see this vertical line, vertical wires, then we can find we can find all literals of the input signals. Okay, then by applying AND gate for these literals, like so this AND is where is this AND gate? So this AND gate is connected to the A bar, B bar, so it's a T junction, right? So it's connected, right? So this is the shape, and then this AND gate makes this main term, this AND gate makes this main term, right? And then also you can find the OR gate here. So we can make the logic. We can make the logic circuit using the basic logic gate like this. So okay, this is a very basic form of the combinational logic. Okay. So sometimes so even though the two-level logic is very common, two-level logics are very common in the logic design, but we can just consider the more complex logic, the multi-level logic like this. So you can find that this is the three-level logic. Okay, what it can be possible? Then actually, the modern systems are very complex. So we can, which means that the combinational logic, and then combinational logic is composed of multi-level logics. Okay, multi-level of basic logic gates. Okay, so this is some another example, and then this example is the multiple output circuit. So you can find the module here. Okay, so and then in this module you can find that so these are input signals, and then these are input port. Okay, then these are output port. And then actually, and if you see this diagram, then you can find that there are multiple inputs and then there are multiple outputs. And then it's common actually in the module, and it's a common. Okay, the multiple inputs can generate multiple outputs. Okay, then, but actually using the multiple inputs, we can define the output values. So the values of multiple output ports. Okay, so this is the priority circuit. The priority circuit just combines the location of the the first one. So it means that if the first one is observed at observed in this input port, so observed for A0, then the priority circuit becomes the 1 0 0 0. So this one represents the location of the first one. Okay, starting from the MSB. Okay, so we can define output. So which means if the inputs are 0 0 0, and then based on the functional specification, so I mentioned that in the priority circuit, the output just exhibit the location of the first one from the MSB. Then what is the output of Y3, Y2, Y1, Y0 for the input 0 0 0 0? H 0 0 0 0. Okay, so we can just generate the output based on the definition. Okay, yeah, I believe this is the 1 0 0 0, right? I don't know, right? So okay, let's see. So this is the truth table, but truth table of this priority circuit. And then if you see the truth table, then you can find that this truth table has multiple inputs. I think it's obvious, right? And then but this truth table also has the multiple outputs like this. So and then also we can find the 1 1 1 1 here. Okay. So in the priority circuit, then we can just the output just indicates the location of port 1 from the MSB. Okay. Then how can you make the hardware, the circuit of this priority circuit priority logic? This is the Boolean equation. Okay. So actually, so in order to make the Boolean equation, so this is the truth table. Okay. So if we but this truth table includes multiple outputs, but we can just focus on a single output for defining the Boolean equation for the corresponding output. So what does that mean? We want to generate the Y0. Okay, then we can just focus on so this value only. Okay, this value only Y0. Okay, so the Y0 can be determined by these inputs. Okay, then what is the Boolean equation about this Y0? So we can use the SOP form, right? So we learned about the SOP form of the Boolean equation, right? So firstly, we can find mean terms that will make output 1, right? For the SOP form, right? So in the truth table, we can find that actually we can find the Y0 is 1 only for the 0 0 0 1. Okay. So what is the mean term of this 0 0 0 1? So this is A3, A2, Okay, this is the SOP form of the Y0, and then once this is done, we can just focus on Y1, okay, and then the Y1 is also determined by the 4 inputs, right? And then we can just apply the same strategy, that's the same SOP form. But actually, but if we just apply the SOP form directly, then we can find oh Y has the 2 ones here, right? Then we need to okay, so Y here, and then this is here, and then if we just select the midterms, then these are midterms. Okay, so then it's Y1, then what's the midterms? Midterm, so 0, 0, 1, 0, and then 0, 0, 1, 1. So this is A3, A2 R, and then A1, and then A0 bar, plus A3 bar, A2 bar, A1, and A0. Right? So this is the SOP form of output Y1. But it can be easily simplified. How? So you know, in these midterms, this these terms are common, right? And then we can find that, so this is the A0 bar and then A0. What does it mean? So this is the A3, A2 bar, A1, and then A0 bar plus A0. So this can be removed. Okay. So this is the Boolean equation of the Y1, and then we can also apply the Y2 and then Y3 for the SOP form. But we intuitively we can know that if the A3 is 0 and then A2 is 1, and then regardless of any values of A1 and A0, then Y2 is 1. Okay, intuitively, because based on the definition of the priority logic, and then if the A3 is 0, A3 need to be 0, and then A2 is 1, okay, the first one from the MSB, then regardless of the any values of in A1 and A0, Y2 becomes the 1. Then we can think like, oh, Y2 equal A3 bar A2. Right, because I mentioned that if A3 is 0 and A2 is 1, and then all cases of A2, A1, A0. So we can make Boolean equation intuitively from the definition or some conditions. Okay. So this is the Boolean equation. So y2 is the same. So y2 is the a3. But a3 is, so you know, if the a3 is the 1, then y3 is also 1. Okay. So this is the priority circuit hardware and then Boolean equations. And then, you know, truth table is so large. Okay. Then we can also simplify truth table like this. Okay. Actually, this is equivalent. So what is different? We can find x here. Okay. What is, and then this x represents the don't care. So which means that, so we know, so for a certain signal, in the digital system, a certain signal needs to have 1 or 0. But sometimes, based on the definition of the described circuit, then if the A1 is 1 and then if A, then regardless of the value of A0, then Y1 becomes 1. So it's a done here. So it can be 0, it can be 1. But if this value is the 0, 0, 1, then Y1 becomes the 1. Okay? So in order to simplify this table, then we can use don't care. Okay? And then it is X. Don't care is X. So it means that this signal, this value can be 1 or this value can be 0. Okay? This is a don't care. So compared to this truth table, so it's actually, as I mentioned, the truth table includes all possible input cases. And then, so there are 4 inputs for this circuit. And then which means that we need to define 16 different cases for the 4 inputs, but it's too large, too long. So we can use don't care like this. Okay. Okay, so this is some example of how to build the logic circuit from the Boolean equation. Okay, two-level logic forms, and then as I mentioned, the two-level logic is a very common form of the Boolean equation. So it is because we can build SOP form or POS form for the Boolean equations. Then so which means that we can make two-level logic for any Boolean equations, right? So SOP form is the AND followed by OR. So which means that it is the AND. So we can just use the main term and then the output of AND gates are OR. So this is the SOP form, and then ORs followed by ANDs. Okay, the first three OR, the next terms, and then the output of ORs are ended. So this is the POS form. So that's what we learned in the previous class, right? But what's this? So actually we can apply the Morgan theorem, right? We can apply the Morgan theorem for this SOP form and the POS form, right? Then we can represent the SOP form by using only AND gate. Okay, that can be possible. Okay, and then what's the benefit? As I mentioned, NAND gate requires less number of transistors. So actually, we can easily and then intuitively build the SOP form and then POS form using AND gate and OR gate, right? That's okay. But we can optimize the SOP form or POS form only using NAND gates or NOR gate. Okay, and then if we just use the NAND gate and NOR gate, then we can reduce number of transistors. That's good. Okay, it's optimized. Well, so SOP form is the most common, okay, because we can easily understand. We can easily understand the behavior of this SOP form and followed by OR. Okay, and then we can. So this is the example, and then this is the example. This is not an example of the SOP form, but this is the example of POS form, right? But so we can easily translate the SOP form or POS form for the two-level logic circuits, right? So this is the example. So this is the POS form, right? Then it's an OR here. Then there is an AND here. That's what I already explained. the previous slides. But so this is another example, and then this is the two-level logic. Is firstly we can use AND gate, and then this AND gate is followed by OR gate. So we can first use AND gate, and then the output of AND gate are OR. Okay. Then actually, so the first thing, so we can build without bubbles, right? So first this is AND gate, and this is OR gate, right? So this is the AND followed by OR. So this is the SOP form, right? So SOP. Okay. But at the same node, so at the same node, we can add two bubbles, right? And then two bubbles is make the original signal. Okay. The inversion of the inversion is same to the original, right? So we can add bubble here and bubble here, right? And bubble here, and bubble here. This is okay. So then why do we add bubbles? So we want to make NAND gate, or we want to make NOR gate, because NAND and NOR gates use less number of transistors, smaller number of transistors. Okay, so this is becomes the NAND gate, and then this is the OR gate, right? And then all inputs are inverted. Then we can apply the Morgan theorem. How? A bar, B bar, C bar equal A, B, C. This is the Morgan theorem. So this direction is okay. So this direction is okay because it's equal, right? So A bar or B bar or C bar becomes the A, B, C. The AND gate, two input AND gate, and then this becomes the NAND gate. Okay, so this gate can be switched to the NAND gate. So in the SOP form, so AND followed by OR. This SOP form can be implemented using only NAND gate by applying the Morgan theorem. And how we can add bubble, or add bubble to this wire. Okay, add the two bubbles for each wire or for this part, and then this is changed to the NAND gate, and then all bar inversion of all inputs can be also changed to the NAND gate or NOR gate by the Morgan theorem. Okay. Here's the form is okay. It's the same. So this is the OR gate, and then AND gate. So and then you can just add the bubbles for this node, and then it becomes the NOR, and then the inversion of AND is changed to the NOR. Okay. So this is the QS form. Okay. So we learned about the bubble pushing. The bubble pushing is very good technique for optimizing the CMOS circuit, right? The basic logic circuit. So actually this is what I already explained in the previous class. Okay, bubble pushing. Okay, the bubble can be pushed to the this is equivalent to this logic. So actually we can push the bubble at the output of the logic gate to the input of the logic gate, and then AND is changed to the OR. And then this direction is also okay. We can find the bubble for the input port, and then this bubble is pushed to the output port of this gate, and then the gate is changed into the or is changed to the AND gate. Okay, this is the bubble pushing. Okay, and then bubble pushing is just the Morgan theorem. Okay, so the bubble at the output port can be pushed to the bubble for the input port, and then AND is changed to the OR, and the OR is changed to the AND. Okay, the inverse direction is the same. Or we can find the bubble for the input port, then bubble is pushed to the output port, and then the OR gate is changed to the AND, and then AND gate is changed to the OR gate. Okay, this is the bubble push. Okay. So then how can we apply bubble pushing? So actually, this is the already optimized circuit, but we can apply the bubble pushing. Okay. Then we can just push this bubble to the here and here. And then if a bubble is pushed, then this is changed to the OR gate, right? And then there are two bubbles at this node, right? At this node, we can find two bubbles, then bubble is disappeared. So this bubble can be also pushed to the here and here. Then we can change that this is F. Okay. Okay. So this is the bubble push. Actually, the Morgan theorem. Okay. So and then now let's define some different signal X and Z. Yeah, I will explain because we have only 3 minutes. So in the circuit that we can use some different symbol. So actually, digital signal. So I mentioned that the digital signal has only two values, right? 1 and 0, right? Only two values, 1 and 0. But now I will explain about X and Z. So you might think, why? So I learned that the signal have only two cases, 1 and 0. Then what about the X and Z? You may think like this, but actually we can use this symbol or this value for representing special cases. Okay. So actually we already learned about the X in the truth table, right? And then truth X means that actually don't care. Okay? But in the circuit, the meaning of X can be different. But the X means that we don't know. So don't care means that it can be 1, it can be 0. But in the circuit, if we just use X, it means that we don't know. We don't know the exact value. What does it mean? So in the circuit, the signal needs to be 1 or 0, obviously, but sometimes, so kind of because of some bugs, some incorrect implementation, the signal, we cannot determine the exact signal value. So in this case, we can use X. So this is the example. So actually, this is not a correct circuit because the output, these are two output of the inverters, two outputs are connected each other. So we cannot know the exact value actually for this case. So this is called the contention. Okay. Then because we don't know the exact value of Y, then we can use the X. Okay. So and then Z. G means the the circuit is disconnected. So which means that the resistance is very, very high. If the wire is disconnected, so we assume that the wire is the zero resistance because the wire is we just assume that the wires are perfect conductors, right? But sometimes the wires can be disconnected. For example, we can use the transmission gate, like here, right? If we use the transmission gate, then the B can be disconnected. Not the transmission. Okay, it's a switch. It's the transmission gate, right? So in this case, the B is disconnected from A. So actually, the transmission gate, so switch. So the resistance is actually infinite. So we assume, okay? Then this is called the Z, the disconnection. So G represents the disconnection. So I will stop here. And I will explain about the detail the meaning of XNZ in the next class. Okay. See you in the next slide.